Welcome to lesson 5.1, which is going to be on similar and congruent triangles. This is the beginning of Unit 5 on trigonometry. So we'll be going over trigonometry for the next 3 days. You'll know when you're successful in this entire unit when you can realistically solve problems relating to similar and congruent triangles. You know the Pythagorean theorem and how and when to use it. You can use the three primary trigonometry ratios to solve right triangles, and we'll get to know SOHCAHTOA. And you'll also know you're successful when you can apply the Pythagorean theorem, SOHCAHTOA, the sine law, and the cosine law to solve multi step problems. So, we're going to start off today by looking at similar and congruent triangles, and then in the next lesson, the Pythagorean theorem. So, the difference between congruent and similar triangles. Well, if two triangles are congruent or have congruency, we say they have the same shape and the same size. They're the same triangle. They might be rotated in different directions, but they have the same lengths and the same angles. So here we can see ABC and PQR. They're actually the exact same triangle, even though PQR is flipped upside down. If we rotated it around, we'd find out that they all have the same side lengths and same angles. So they're congruent triangles. What we're going to be spending most of our time on is similar triangles. In similarity, we have the same shape, but we have different sizes. So our side lengths are going to be different, but the angles are going to be the same. So here, ABC and PQR have the same shape, but they're not the same size as PQR is bigger than ABC. And so we'll explore this a little bit more. Triangles are similar if they have the same shape but are different sizes. And not only are they different sizes, but we're going to find out that the sides are actually multiplied by what's called a common scalar. Or when we put them in a ratio, the ratio is the exact same. One really important note here, the order in which we write the vertices is very important. So we have to line up our angles in the two triangles. So right now, AB would be similar to ST, AC would be similar to SU, and BC would be similar to TU. And similar triangles corresponding or matching sides are in the same ratio or multiplied by a common scalar. And we'll explore that very shortly. And the corresponding angles are all going to be the same. So in our above example, angle B would be equal to angle T, angle A would be equal to angle S, and angle C would be equal to angle U. In terms of what a common scalar is, a common scalar is the number that each side of the smaller triangle is multiplied by to obtain the sides of the larger triangle. So I'll show you how to do that shortly. Also, really important to remember the sum of the interior angles of a triangle equal 180 degrees. So in a triangle, we'll have three different angles. We'll add those three angles up, and they'll always equal to 180 degrees. To show two triangles are similar, it is sufficient to show that one of the following is true. So we're going to look through three different examples. If we can say that the three pairs of sides are in the same ratio or multiplied by the same scalar, this is known as side, side, side. So sometimes we'll see it written as SSS. And here's an example down here where the corresponding sides are all multiplied by the same common scalar to get from the small triangle to the large triangle. To find the scalar, set the corresponding sides as a fraction or ratio, with the larger side as the numerator and the smaller side as the denominator. So here, our corresponding sides, we're going to find out what the common scalar is. So on our larger triangle, side ST, which is 6, is matches up with side RP, which is 3, so 6 over 3. TU and RQ match up, so that's 8 over 4. And finally, SU and PQ match up, so we get 10 over 5. If this is a similar triangle, then the scalar will be the same for all three sides. And in this case, if we wanted to find that out, all we have to do is 6 divided by 3, which will give us 2. 8 divided by 4 will also give us 2. And finally, 10 divided by 5 would also give us 2. So the common scalar in that example is 2. Two pairs of sides are in the same ratio and the contained angles are equal. This is known as side angle side. And it's the second way that we can prove that two triangles are similar. So, an example of this would be this triangle here, where we've got a small triangle of LMN and a large triangle of LPQ. We can see that the vertex L is shared by both triangles, so it's the same angle. And if we notice that side LP and LM are the same and multiplied by the same scalar as LQ, then we're going to have similar triangles here. So side, angle, side. The angles contained between the two known sides. And so here, if we do 10 plus 8, well, the side here, the large triangle, is 18. So we'll do 18 over 10. And that should equal 5 plus 4, which is 9, over 5. And if those are the same scalar, because we have the same contained angle, then we've proven that this is also a similar triangle. So 18 divided by 10 and 9 divided by 5 will both give us a scalar of 1.8. So our common scalar, or the number that the smaller triangle sides are multiplied to give us our larger triangle sides, is 1.8. The third proof that we can go through to show that a triangle is similar is when two pairs of angles are equal. When two pairs of angles are equal within the triangle, that will mean that all three angles will be equal, since the interior angles must add up to 180 degrees. If two of the angles are the same in both triangles, then that third angle also has to be the same. And this is going to be known as angle, 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 or AAA. So here we know two angles and two angles. These two angles and these two angles are the same. So that third unknown angle must be the same in both as well. And we can use the interior angles of a triangle adding up to 180 degrees to prove that. So if we do 180, it should equal 104 degrees plus 21 degrees plus our an unknown angle here as well. So we can actually solve for that, and it'll be the same in both triangles. So this is like 180 minus 125. So our missing angle there is 55 degrees, and it would be the same in both triangles. This would also be 55 degrees. So since all three angles are the same, then they must be similar triangles. So a little summary there. We can prove that triangles are similar using SSS. That's when the three pairs of sides are in the same ratio or multiplied by the same scalar. We can have side angle side or SAS when two pairs of sides are in the same ratio and the contained angles are equal. And then finally, we can do angle, angle, angle or AAA. And that's where two pairs of angles are equal, which means as well that our third angle is equal. All right, so that's a little introduction. And I'm going to stop the video there and I'm going to do another video starting up at example number 1. So join me to see the examples in a couple of moments.